In this video, we'll take an introduction to combustion reactions. Combustion reactions provide energy, hydrocarbon fuel is burned, and there are many examples of combustion reactions. I have three on the board here. First example, I want you to imagine that you're cooking on a stovetop and flames are coming out of the stovetop to boil water, cook your pasta, whatever else. The energy comes from oxygen gas is coming in from the atmosphere. Natural gas or methane is a molecule CH4, a molecular compound, coming in. Then they react with each other to produce heat, carbon dioxide, and water vapor. And then another example is the combustion of propane. A barbecue grill, for example, a propane tank provides propane gas. The propane has a chemical formula of C3H8, reacts with oxygen in the atmosphere. You spark it to cause that reaction to occur. Heat comes out. This is a very bad drawing of a barbecue grill. And carbon dioxide and water vapor are released, along with the energy to cook your steaks and so forth. And then the last example over here is you're driving in your car. You have octane fuel. That's one of the main components in gasoline. And octane has a formula of C8H18. That fuel gets injected into the chambers in the engine. Oxygen gas comes in, the spark plug sparks it, causes the reaction to occur. And once again, we get carbon dioxide and water vapor coming out of the exhaust and energy to provide energy to move the car. So now let's look at these examples over here and let's write what's called the balanced chemical equation for each. In the case of natural gas, our fuel is methane, which is CH4. So I have CH4. I'm going to put an underline in front of you here. And then I have oxygen gas from the atmosphere. And then I'm going to produce carbon dioxide. I'm going to produce water vapor. And I'm going to produce energy. Now, we have to write what's called a balanced equation. CH4 is a molecule that contains one carbon atom and four hydrogen atoms. For example, this model right here, one carbon atom, four hydrogen atoms. And we'll get into bonding and Lewis diagrams later on, but for right now, this has one carbon atom and four hydrogen atoms. I'm just going to represent that molecule like that. Oxygen gas in the atmosphere is diatomic. Oxygen atoms do not like to be by themselves. They will partner up with other oxygen atoms. So here are two oxygen atoms. And during a chemical reaction, we break the molecules apart, but we then reconnect the atoms in different configurations. We're going to get carbon dioxide, which is a carbon atom, an oxygen atom, and an oxygen atom. And we're going to get water, which is an oxygen atom and two hydrogen atoms. Now, we need to balance this, meaning you'll notice that I have a total of four hydrogen atoms here in my original molecule. Therefore, I'm going to end up with four hydrogen atoms. But over here, there are only two hydrogen atoms. So I need to draw another molecule of water, another H2O. That way I've didn't lose any hydrogen atoms. Now, as far as carbon atoms, I have one carbon atom here, one carbon atom there, that's fine. Oxygen atoms. You'll notice now I have 1, 2, 3, 4 oxygen atoms. So oxygen atoms don't magically appear. What that means is we must have started with two molecules of oxygen. And so we're going to write a balanced equation. One molecule of CH4 is going to react with two molecules of O2 to produce one molecule of CO2 and two molecules of H2O. Now, it's impractical to talk about molecules, but mole ratios are the same as molecules ratios. So we can say that we have 1 mole of methane will react with 2 moles of oxygen gas to produce 1 mole of carbon dioxide and 2 moles. Let me scooch this up over here. Get that out of the way. Give me some room here. 2 moles of H2O. And that's what that's our recipe, so to speak. Let's go ahead and do the same thing over here for the combustion of propane. Propane has the formula of C3H8. I'm going to put an underline in front because to remind me that I'm going to have to balance this. It's going to react with oxygen gas, O2, and it's going to produce carbon dioxide, CO2, and water vapor, H2O, plus energy. Heat energy is going to come out. We'll do energy calculations later. Now we have to balance this. And I can draw all the atoms, but let's try to do this without drawing this there. I have 3 carbon atoms. Here, this only represents 1 carbon atom. Remember, CO2 is 1 carbon atom and 2 oxygen, 1 carbon atom. So if I have 3 carbon atoms, I must end up with 3 carbon atoms, so I'm going to balance the carbons. Carbons are taken care of. Now let's worry about the hydrogens. I have a total of 8 hydrogen atoms here in the beginning, but there are only 2 over here, right? The water molecule only has 2 hydrogen atoms. So I need to have 4 of these molecules of water to account for all the hydrogen atoms, so that no hydrogen atoms disappeared. Now let's worry about the oxygens. On the right side over here, I have 3 molecules, but each molecule contains 2 oxygen atoms. So this part right here represents 6 oxygen atoms. And then here I have 4 water molecules. Each molecule contains 1 oxygen atom. Right here's a molecule, 1 oxygen atom. And I have 4 of them. So that accounts for 4 oxygen atoms. So my products have include a total of 10 oxygen atoms. So I must have 10 oxygen atoms to begin with. And so I'm going to put a coefficient of 5 here because 5 times 2 is 10. And so this is a balanced reaction. Let's go ahead and do over there. So my theoretical ratio here, right, it's understood that there's a 1 there. So my recipe, so to speak, is that if I have 1 mole of methane, it will react with 5 moles of oxygen gas. It'll produce 3 moles of carbon dioxide, and it will produce 4 moles of water vapor. Okay. I'm going to erase this part right here. I hate erasing things. This is my recipe. Now, I can do the same thing down below over here for octane. In the case of octane, I have C8H18, and then I have oxygen gas, and it's going to react to produce carbon dioxide and water vapor, H2O, plus energy to move the car. Now, I want to get my molar recipe, my theoretical recipe. What is the recipe here? If I react 1 mole of this, how many moles of oxygen do I need? If I react 2 moles of this, how many moles of carbon dioxide come out? My recipe. Let's balance the carbons. I have 8 carbons over here. I only have 1 carbon represented there, so I'm going to put a coefficient of 8. That way the carbons are balanced. I have 8 carbon atoms on both sides. 18 hydrogens here. And I need to have 18 hydrogens, but there's only 2 hydrogens there. I'm going to put a coefficient of 9 in front, and that'll balance the hydrogen atoms. Oxygen. This is going to be a doozy. I have 2 oxygen atoms here, but over here, this represents 16 oxygen atoms. Right here, 16 oxygen atoms. And this represents 9 oxygen atoms. That's a total of 25 oxygen atoms. I have 2 over here, so I'm going to put a coefficient of 12 and a half. 12 and a half times 2 is 25. So my recipe is, if I have 1 mole of C8H18, then I'm going to need 12 and a half moles of oxygen gas. It'll produce, I'm going to erase this now, that already served its purpose. It's going to produce 8 moles of carbon dioxide, and it's going to produce 9 moles of H2O. If I were to do a reaction, and if they said how many moles of carbon dioxide come out if we reacted 2 moles of C8H18, well, 1 mole gives you 8 moles of that, so 2 moles of C8H18 would give you double, 16 moles. It's just simple ratios. So we'll leave it at that. That's a brief introduction to combustion reactions and balancing combustion equations.